We're going to look at the definitions of trigonometric functions. Now, I have nothing against triangles. The definitions of sine and cosine, etc., as opposite over hypoposite and so forth, are perfectly valid and very handy. However, in this course, we're going to primarily use the circular definition of the trigonometric functions. You should be familiar with the circular definition, but I'm going to give you a rundown here anyway. We start with a unit circle, a circle of radius 1 centered at the origin of an xy coordinate system. Any point on this circle can be reached by a line segment extending from the origin to that point. That line segment will make some angle which we'll call theta, as measured counterclockwise from the positive x-axis. So let's make a note. Theta is measured counterclockwise from the positive x-axis. None of this works if theta is measured in a clockwise direction or from any axis other than the positive x-axis. Now, with that convention, our definition of sine of theta and cosine of theta, our definitions of sine of theta and cosine theta are very straightforward. That point xy, if the point is xy, then the cosine of theta is going to be x, the sine of theta is going to be y. Now, that reconciles just fine with the triangular definition of the trigonometric functions. We have a perfectly good right triangle here, and its hypotenuse is 1 because this circle has radius 1. This is a radius of the circle, so the hypotenuse has radius 1. So if you take the adjacent side divided by the hypotenuse, that's going to be x divided by 1. And that is the definition of the cosine function in terms of triangles. The only difference is that x here, in this picture at least, is a negative number. And your triangle definition doesn't accommodate positive and negative numbers. It accommodates only positive numbers because we're talking about the lengths of sides of triangles. So the big advantage to the circular definition is it automatically accommodates positives and negatives. And as you know, if you've done statics, for example, you have to always be worried about whether you have a positive or a negative value, whether the side of a triangle goes in a positive or a negative direction. That's not something you have to worry about with the circular definition. So again, for any point on the circle, we do a radius from the center of the circle to that point, theta being the angle from the positive x-axis. Then the x-coordinate is the cosine of the angle, the y-coordinate is the sine of the angle. Now, if we have a circle of radius a, then what are the x and y coordinates? Well, it's fairly straightforward. If a circle has radius a, then it's a times as big as a circle of radius 1, which means you simply scale the picture up or down. Instead of x, you're going to have, instead of x being the cosine of theta, in this case x is going to be a times as big as the cosine of theta because x is going to be a times as big as it would have been over here. Similarly, y is a times the sine of theta. So if the circle has radius 2, the x-coordinate of this point is going to become twice as great, so it's going to be equal to twice the cosine of theta. Another really good thing about the circular definition is we can imagine this point moving at some constant velocity around the circle, again and again around the circle. What's going to happen to the y-coordinate as we move from here all the way around the circle? Well, as we move from here, the y-coordinate is going to increase But of course, as we get toward the y-axis, we're moving mostly in the x direction, so the y-coordinate is going to decrease more and more slowly. Going to increase more and more slowly. And then as we move from here to here, the y-coordinate will decrease slowly at first because we're moving mostly in this direction, but by the time we get here, it's going to be decreasing very quickly. And you can trace the motion around here, think of what would happen to the y-coordinate. Similarly, the x-coordinate, starting from here, would start at this point, move to 0, move to the negative position, move back to 0, and then move to the positive position. Starting out slowly because we're mostly moving in the upward direction, but moving very quickly here, and moving more slowly when we get over here, more quickly when we get down here, and so forth. I'm not going to go into great detail with that description, but the motion that you would get if you followed the x-coordinate here would in fact be simple harmonic motion, and that's the way a pendulum, for example, moves. Or if you think of the y-coordinate, that's the way a mass oscillating up and down on a spring moves. So the circular model has a lot of applications, that being one, another being to rotational motion. And we'll delve into that in much more depth, but just to establish that there are good reasons to focus on the circular definition in this course.